Okay, so let's do this this first equilibrium example. And in this problem, we have a gorilla and a person standing on basically a seesaw, basically. And there's some pivot point here around which the seesaw can kind of go down or up, depending on the balance between the two, the gorilla and the man. Okay, so what we're told is the gorilla has a mass of 210 kilograms, and we're just going to call it big M for now. And our person has a mass of 70 kilograms, which we'll just call little m for right now. And we're also told the gorilla is 1 meter away from that pivot point. Okay? And we want to know, where does this person have to stand to make this system be in equilibrium, to balance the system, in other words. Okay, so this person's going to need to stand some distance we'll call x away from this pivot point here. Okay? So what are the forces acting on this seesaw then? Well, we have the gorilla's weight acts downward here with the force of big M G. The person's weight acts downward with a force of little m G. Okay, but there's one more force here acting on the our massless seesaw. Okay, gravity doesn't act on the seesaw because it's massless. Okay, but the weight of these two, the gorilla and the person on the seesaw, pushes down on the pivot point, which in turn pushes up on the seesaw. So there's a force up here from the pivot point, which we'll call F. Okay? So there's the setup for our problem. And so our two conditions for equilibrium are, first of all, our forces have to add up to 0. And the other condition is that our torques have to add up to 0. Okay? Now, for this particular, the first part of the question, we're asked, where does the guy have to stand? And really what we need to do then is we need to balance the torques here. So let's apply our first equilibrium condition to part A. So our torques have to add up to 0. And remember, when we're doing problems like this, we can pick any point we want is the pivot point. Okay? Now, for this particular problem, the actual point of contact here is probably the best point to pick as the pivot point. Okay? Fairly obvious in this problem, but as we do some other examples, it's a more arbitrary choice about where we want to pick the pivot point. Okay? So here's our pivot point. So we need to calculate the torque about this point due to these three forces. Okay? And what we'll do is we'll call, I can't remember the convention the textbook uses, but what we're going to use is we're going to use counterclockwise is a positive torque, clockwise is a negative torque. Okay? So the torque, remember, is when forces are applied perpendicularly like this, it's the distance from the pivot point times the force. Okay, that's our definition of torque. So the torque from this force here is the force itself, M big mg, times the distance from the pivot point, which is 1 meter. Okay. Now, what about this force? What about the force from the pivot point on the board here? Well, it's acting right on the pivot point. So our distance r from the pivot point is 0. So this force applies 0 torque. It neither will cause a counterclockwise rotation or a clockwise rotation. So 0 torque from that force. Now this guy, this is a clockwise torque, so that's negative. So the torque from that guy is minus little mg times the distance from the pivot point, which we called x. Okay, and that has to equal 0. So the g's cancel. And we can now put in our values for big M and little m. We have big M is 210 kilograms times 1 meter. And once you add this to the other side of the equation, this has to be equal to little m times x. Little m is 70 kilograms times x. So you solve this algebra situation here, we get x is 3 meters. Okay? So that's not a big surprise that we get the answer 3 meters. The gorilla is 1 meter from the pivot point, and he has 3 times the mass of our man. So our human here has to stand 3 times as far away from the pivot point to balance that situation. Okay, now part B asks us to calculate the force applied at the point of contact on the pivot point. Okay, this force F in other words. And to answer this question, we're going to apply our second equilibrium condition, this one. So our net force has to add up to 0. And our convention, as usual, is going to be upward force is positive, downward force is negative. So our upward force is F. And then we get 2 downward forces. Big mg, which means we get a minus big mg, and minus a little mg for the other force. So in other words, the force applied at that contact point has to equal the weight of the gorilla plus the weight of the human. Okay? So that's not a big surprise. We have the gorilla's weight pushing downward, the human's weight pushing downward, and this pivot point therefore has to support both of their weights. So it's big mg plus little mg. And when you do this calculation here, big M, remember, is 210, little m is 70, g is 9.8. You get the number 2740 newtons, which is basically, it's just the combined weight of the gorilla and our human.